Welcome to this video on systems of ODEs. Before we get into the mass of this, I want to just take a look at an intuitive example of a system of ODEs, which is a population of rabbits and foxes and how they develop over time. If you think about rabbits and foxes for a second and imagine them living in an environment together, then you'd expect the population of rabbits to be dependent on, first of all, how many rabbits are in existence, and second of all, how many foxes are in existence. Rabbits need other rabbits to breed with each other. Other rabbits also compete with them over resources like food. And so the number of rabbits that already exist will definitely affect the growth of the population of rabbits. On the other hand, foxes, which will feed off rabbits and eat them, is going to impact their population. And so if there are lots of foxes running around, then that is going to actually decrease the population growth of rabbits. And then if you think about foxes as the focus, then the more rabbits that we have, the more food is available for the foxes. That's going to grow their population. But as the population of foxes grow, that's going to mean there are more foxes hunting the rabbits. So rabbits are going to decrease. And we have essentially this system of derivative, which is population growth of rabbits and foxes that depends on how many rabbits and foxes that are already in existence. And so actually in the real world, there are lots of things where the derivative is based off the function of interest itself and something else. And population is just one such example of this. And we call this a system of ODEs when you have the derivative of x is dependent upon the function x and the function y, and the derivative of y is dependent on the function x and the function y. And in this case, the functions are the populations of rabbits for x and foxes for y and how they change over time. And then of course the population growth is dependent on both of those two factors. And so what we're looking at in this video is how can we actually solve these systems of some unknown function that we have information about its derivative and the way it is being impacted by, in this case, the population of rabbits and foxes. And we're trying to work out what this system will actually look like over time if we were to let I guess the system come to maturity and let just time play out with a starting point of say 50 rabbits and 50 foxes. So the way that we do that mathematically, and also we're looking at the simple case of linear ODEs, so we just have the population being dependent upon some constant multiplied by xt, some constant multiplied by yt. So it's quite simple and it's a linear form of ODE. And the way that we solve that is by representing it in this matrix form where the derivative of x is equal to a times x. And here x is the function of time and y is a function of time. And then a, b, c, and d are just constants, just numbers. Okay, so what would we expect? We'd expect to find solutions of this form. Because if the derivative is equal to some constant multiplied by itself, then of course the exponential function is a prime suspect, as when you differentiate the exponential function, you get back another exponential function. And the way that we actually determine what these specifically are based on the A, B, C, D matrix is by working out the eigenvalues and the eigenvectors of A. Okay, so I want to explain that a little bit more. If we look at this here, x prime equals to ax defines our system, and we're hunting down solutions of the form alpha multiplied by e to lambda t, where alpha is some real number. And so we expect our x vector to be equal to alpha 1 e to the lambda t and alpha 2 e to the lambda t. So both our population x and population y is dependent upon time in a relationship that looks like this. And they have different coefficients out the front, alpha 1 and alpha 2. Notice there's no lambda out the front here because lambda, when it's differentiated, will impact the coefficient in the front here. But beforehand is just some constant alpha 1 and alpha 2. And then of course the exponential needs to be held constant with the lambda t up in here because if this exponential changed when you differentiated it, you wouldn't have our linear system where it's just equal to a constant times the previous exponential. Okay, so anyway, proceeding on with this, we can put our vector v as just our alpha1 and our alpha2 as those constants that are in front of this exponential. And then now we have x equal to the vector v multiplied by e to the lambda t. And when we differentiate x prime, the only thing that changes is the lambda comes out the front here. Okay, and we can plug this now into the system. And the system was that x prime is equal to a x. So we know x prime is this, so we can plug that directly in. And that gives us x prime here is equal to ax, and x in this case is just this. Now, dividing both sides by e to the lambda t gives us lambda v is equal to a v. And hopefully, when you stumble upon this in the matrix world, what is really coming to the forefront of your mind is that this looks like eigenvalues and eigenvectors, and that's because it is. This is by construction what an eigenvalue and an eigenvector is. It's when you multiply a matrix by a vector, and the way that that matrix transforms the vector is only by scaling linearly that vector. It's just scaling it up or down by some constant. And if that is happening when your matrix multiply a vector, this is an eigenvector, and then the scaling factor is your eigenvalue. And the fact that our solution process is leading to this means that we can find out the solutions by finding out just the eigenvalues and the eigenvectors of that matrix. And that will give us our v, those coefficients out the front, and our lambda, the specific exponential index coefficient of t. And that's essentially the idea of this, is if we can work out the eigenvalues and eigenvectors of A, then we have information about the solutions to our system. Okay, and as our system is linear, adding solutions together will still be a solution. So if we work out multiple eigenvalues and vectors, and usually you can find two real eigenvalues with eigenvectors corresponding to it, stacking them on top of each other will give us the general form of the solution. So x of t is going to be equal to alpha 1 e to lambda 1t plus beta 1 e to lambda 2t, and then y of t is alpha 2 e to lambda 1t plus beta 2 e to lambda 2t, where this is the eigenvector for lambda 1, and then the other eigenvector for lambda 2. And that is our solutions to these two ODEs that are actually integratedly connected to each other. Once we have these solutions, notice that they don't depend on each other in terms of x and y. They just depend on t, but the way that they unfold in terms of their derivatives and that system above is going to be accurate, because we derived it from the definition that their derivatives over time will always match up to each other. Okay, so let's take a look at an example of this. So if we were given a question like this, where the derivative of x is equal to minus x of t plus 4y of t, and the derivative of y is equal to minus 2x of t plus 5y of t, then we can put it into our matrix form, where the derivative is equal to minus 1, 4, minus 2, 5, minus 1, 4, minus 2, 5 of x and y. And then we can focus on solving that matrix A in terms of its eigenvalues and eigenvectors. It's not the purpose of this video, so I'll just skip forwards with the answer. You get eigenvalues 1 and 3, and their corresponding eigenvectors v1 and v2. If you're not sure how to do that, then check the other video on linear algebra that will be up about how to calculate eigenvalues and eigenvectors. And now we have our solution, putting that into this expression here, that xy is equal to alpha 2, 1 e to the 1t plus beta 1, 1 e to the 3t. And once you expand that out, you get this. All right. So what we'll do from here is actually an analysis of the phase portrait of this. And phase portraits is a way of understanding the dynamics of X and Y. So if you were to start with any initial value condition of X0, Y0 of something, what would your dynamics of X and Y be over time in this system of these things relating to each other? So when time is equal to 0, you've got X of t is equal to 2 alpha plus beta, and Y of t is equal to alpha plus beta. And what these alpha and beta are determinants of what your starting conditions are for X and Y. And you can then say, okay, if I started with X is 100 and Y is 200, what would happen over time if they are behaving in this manner? And the way that we graph that is using a phase portrait. So this phase portrait below is graphing this particular example. So I'll explain how this graph is constructed. First of all, you need to draw the eigenvectors. So the eigenvectors are 2, 1, and 1, 1. And if we draw 2, 1 first, that means that it's going 2 units in the horizontal axis, 1 unit in the vertical axis. And then this vector here is the eigenvector direction. This line here is categorized by the eigenvector direction 2, 1. And then similarly drawing our eigenvector 1, 1, we get this orange line here, which is a line categorized by the direction of 1, 1. And then I put lambda equals 3 and lambda equal 1 to match the eigenvalues to this eigenvector. And what we're wanting to graph, maybe just to give you a bit of an overview of phase portraits, is that we have X and Y on our horizontal and vertical axes, and we actually care about time as almost a third dimension, but the way that we portray time as this third dimension is with arrows. Where time progresses, it follows the arrows of our diagram over time. So X and Y will follow this relationship together over time in this direction. And the way that we determine our phase portrait in this case is that this the eigenvector that has the larger eigenvalue will be the dominant eigenvector and the dominant direction, which means that as time progresses, this is going to dominate our X of t and Y of t expression. And so the only thing that matters is our plus beta, which is a relationship of 1 to 1 here. And this is going to pale in significance to this when t is large. And so they will be growing in a way that is 1 to 1 relationship. And that is represented along this line here, lambda is equal to 3. And the opposite is true for an exponential. When t is really small, then this will be the dominant eigenvector for small t. And so it will tend towards the eigenvector 2, 1, which is characterized by the lambda equals 1 line. And so for small t, it'll start off in the direction of following this line. And then as t gets larger, it will then prioritize the other direction, which is this way. Okay, and with phase portraits, they are usually fixed points or equilibriums, where the idea is that at this fixed point or equilibrium, whatever you want to call it, the dynamics of the system are steady and X and Y remain constant. And if we look at our X of t and Y of t, that will only be a fixed point and steady system when alpha and beta are both 0, i.e. when X and Y are both 0. And if X and Y are both 0, then the system will not grow and it will remain fixed at 0, 0. And so our system here has a fixed point at the origin here, 0, 0. But in this case, it's a unstable fixed point, an unstable equilibrium, because as soon as you deviate from 0, all of your pathways will lead away from it, exploding as a system, as opposed to a fixed point where the pathways lead towards it, and that time will perhaps decay an exponential into your fixed point. So this is an example of a unstable equilibrium at 0, 0, and some pathways have now been drawn of how x and y would operate over time if you were to pick a point. So notice we have this one here where you start off going towards the eigenvector with lambda equals 1, and then you switch across to eigenvector lambda equals 3. If you start in between them, you have the same thing happening, where you tend towards 1 at the start, and then you go towards lambda equals 3 in a parallel way. And yeah, this is an example of a phase portrait that is analyzing the dynamics of this system above. All right, that's the end of this video, which is looking at systems of ODEs and a example phase portrait corresponding towards it. I hope you found it helpful. Thanks.